So today I would like to have time for research methodology behind protein crystallization. Not only protein crystallization, but also practical research methodology, as I told you. So we can discuss the vocabulary itself and thinking itself, not just learning something new, but critically thinking how you can learn based on your own vocabulary. That will be the topic for discussion. Annie, you know something about protein. Last time we talked about protein structure and hydrogen bonding and atomic model in physics and chemical bonding model in chemistry and protein structural category or hierarchy in biology. But crystallization may be new to you. Crystal, you have learned from chapter 1, 2, but crystallization is a little bit something new. To you, what is crystallization? In simple terms, in simple English.
I think after purification, after gene cloning and purification, we got protein, and we make how is a method to know about structure.
To know about structure,
Protein structure.
we need a protein structure. We need protein crystal. So to you, crystallization may be the way we can obtain crystal. Crystallization is the way to get crystal out of some starting material. But let me ask you this question again to articulate your own answer you already made. What can be starting material in the case of protein crystallization?
What is the first step?
At the starting of protein crystallization or any kind of crystallization, you need a material.
Yes.
But unlike diamond, unlike graphite,
Yes.
unlike sugar is also crystal. Also table salt, NaCl is also crystal. But those materials, we just need sugar in water, NaCl in water. But what about protein? Imagine or guess or remember what you actually did have in terms of protein.
The material for protein crystallization, the first we need to get the purified protein.
Purified proteins in which condition?
In buffer.
In buffer,
Yeah.
to make protein happy.
Yeah.
If they are not in buffer, proper buffer, protein may be degraded or may not function properly. So they should be in proper buffer, proper pH and proper salt. So always we start protein crystallization with protein stock solution, of which component may consist of some buffer and not necessary to say protein itself. Okay, so over time and over space, we may go through some process and eventually we have crystals out of such a starting material. Okay, but to play with such a crystallization, we also need to add something more or to change something to change solubility. Solubility is the critical parameter you have to consider during purification step. Also, eventually, solubility matters significantly to have crystals out of protein stock solution. We'll talk about through this process, and based on your own former experiences, let's build some new understanding. Okay. That will be our purpose. Anyway, let's have photos of protein crystals. Have you ever watched this kind of photo gallery? Or?
Here is a crystallography picture.
Anyway, I took this photo from book chapter.
Yeah.
If you read book chapter, you may have some hint, but unless you read book chapter already, I'll give you some idea. Anyway, here we have variety of forms. Here some crystals in regular shape, but these are not very regular. It were like needle, but grouped together in some way. And the other is very clean, but very thin in terms of thickness. This side thick, but the other side wide. And this mostly in aggregate, not well-formed phase. And this number 6, well-formed crystals with aggregate as a background. So we have variety of conditions, but what is common here is if you get photo closely, all have this kind of boundary. It's kind of well drop. You use well plate for cell culture or drug screening. Yes. 96 well and 24 well plate. We have used such a well plate for variety of crystallization condition. But what condition do you have? I'll tell you. Usually during protein purification, what can you change or what factors do you have in terms of changing solubility? Many factors we have actually, but I'm trying to.
In my case, sometimes I use some kinds of vector in PET 28A, PET 2022, and I just working on this vector.
Vectors, many vectors usually, but out of such a vectors, eventually you have protein expressed. Yes. But anyway, out of any kind of vector, we will have recombinant protein. Yes. You are talking about recombinant proteins, not natural one, or but out of such a recombinant proteins, we have different extra amino acids. Depending on such a extra amino acid, we may not have same pI or we may not have same solubility for the same buffer. So proteins, as defined by its sequence, has unique property called pI or solubility, depending on solution. But solubility itself is not only changed by sequence itself, but also changed by physical parameter like temperature. Even sugar, table salt, they do not have same solubility. At high temperature, what do you expect from sugar for cooking?
Cooking, the color change. The color when sugar at a higher temperature, the color of sugar is more dark and.
That's for heating the sugar itself. Yeah. But what about sugar in solution?
Solution is more faster. Solubility faster in higher temperature.
Faster. You used faster. That is another topic, but let's talk about this first. Anyway, I would like to discuss your experience under the light of some theory behind protein crystallization. But when I introduced protein crystallization as a title, I added in space and in time. Here, I was showing in space, dimension in space. Actually, all of these drops are in the order of millimeter size. We are watching these drops under the light of microscope. And actually, crystals are order of few hundred micrometer, because these drop millimeter, the crystals are in several 0.1 millimeter or several hundred micrometer. So that's the point I'd like to show you in terms of space, but you said faster. Faster means in time.
Yeah. Right.
Crystallization issue in time. Usually most of drops were crystallized in few days, but for particular proteins it may take over weekends, several weeks, and even over several months. But quicker is not always better. I'll tell you later, but sugar solution as your common crystallization experience. At high temperature, we have higher solubility. If I gave you quick answer, over time, not over time, over temperature, solubility and temperature. Higher temperature, more amount, sugar, temperature, degree. Okay? And close to zero, we have very little, even under zero, water is frozen, so we cannot have any soluble part. But anyway, 100, we have certain solubility, and above 100 we do not have any water. So between 0 and 100 we have some amount for sugar which can be dissolved in water. But this is about amount of sugar which can be dissolved in water, or concentration. Concentration or amount of sugar which can be dissolved in water. But you said faster at higher temperature. It can be true, but point is solubility itself neither faster or slower. Solubility is the concept which does not involve any time. That is the tricky part. But in practice, higher solubility may imply faster solubilization. And the way we can crystal sugar crystal out of sugar solution is like this. If we dissolve huge amount of sugar powder, very small tiny crystal. Actually sugar powder is consists of many tiny, not complex, pure sugar crystal, but in very small size, several hundred micrometer or even down to 10 micrometer. But if you look at sugar powders using microscope, you may see some particles. But by dissolving sugar, let's say 80 degree, you can say several milligram, 100 milligram there. I don't remember exactly, but if we dissolve water, water is 1000 milligram per cubic centimeter, right? That is the density of water. But sugar can be dissolved in comparable amount in this water, 1 gram of water and several hundred milligram of sugar can be dissolved at higher temperature. And if we decrease temperature, the amount can be dissolved can be less than original. So this difference cannot be dissolved in water. As a result, we should have something out. What will happen with this kind of something out?
It means it's freezer a little bit.
Freeze, you said. But this is not the freezing point.
Oh,
Yes, that's the better word. Precipitation. Precipitation and powder. Initially, powder. Powder, precipitation, they are close to each other in terms of not well-formed crystals or not in very good size. Precipitation of sugar may not look like this, but in terms of nature, in terms of its aggregative nature, they are like this. But they may not be like that or either that. Okay, so crystal, you know what sugar crystal look like?
I'm not sure.
Even sugar crystal with careful control of temperature, you can make big as large as several millimeter. But normally you are not watching sugar crystal in such a big size, but just powder. Any from this one, your answer pastor should be understood not in terms of time, but in terms of your knowledge about solubility. But usually higher solubility means faster solution. Is that correct? And you brought very good keywords. Powder, precipitation, okay, and faster. So what will happen to protein crystallization if we have faster or very quick aggregation or precipitation?
Maybe there is some change in function, protein function.
Mm.
When we increase faster, when we change temperature or change pH, it's really easy to make change protein function.
Basically, either it is functioning or not.
No.
Simply aggregate may not function properly. But crystal itself, even in crystal lattice, but it's a perfectly functioning protein. So as you said, protein crystal may function in crystal, but it will not function as protein when we have precipitation or aggregation. So if you have dramatic change in solubility due to quick change in temperature or quick change of some precipitant, I'll talk about precipitant later, but anyway, on top of protein solution, we should add some precipitating agent to change solubility. So basically, temperature can be physical parameter. Also here, precipitant concentration can be another physical parameter. And we have several many, like protein itself. So protein itself we will talk about later in terms of protein solubility diagram. Okay? That's why I used space and time, and you answered very nicely in terms of time using the keyword faster. And I'll talk about kinetic part right now, but I'll talk about space part. Here, last time we talked about crystal size in terms of angstrom, protein size in terms of angstrom, 30 to 6 angstrom in this direction, and 125 in this direction, and 150 angstrom. To have crystals, we should have such a building block in space. Okay.
Yes.
I'll talk about this, and if you look at some textbook figure, this is protein, and this is presentation of protein. drawn in ribbon diagram, what is character or characteristic feature of this diagram? What can you notify?
Here is just one protein, but we can see this protein structure in different way, different dimension.
Different dimensions, but
And,
in which dimension, first of all?
2D.
Two dimension, yeah. Two dimension, yeah. Two-dimensional lattice.
Yes.
Technical word is lattice, two-dimensional lattice. Along X and along Y,
Yeah.
we have some regular arrangement. Yeah. That is good point. But what about three-dimensional crystal? So we will have another direction here, this perpendicular direction. We have packing. Here, actually, protein is not planar material. It's a three-dimensional material. We have some volume, and we have some packing along this direction too. Okay? So these can be arranged in three dimensions. These can be arranged in three dimensions. All these can be arranged in three dimensions. But repeating unit will be single molecule like that or larger molecule like that. So using our protein solution, what we are trying to do is building the assembly of regular arrangement in three dimensions. So in space, we have some repeating unit called cell parameters. A, B, C, alpha, beta, gamma. Do you remember?
Yes.
So along X and along Y, not necessarily Y, but Y in orthogonal dimension, but Y in B direction. That is tricky. A and B may not be orthogonal. Any A, B, C in angstrom. That is so-called cell parameters. Here we are just giving numbers in shape, but specifically we should have A direction, B direction, C direction. In three dimensions, we should have regular arrangement not only in X, but also in Y, but also extra one is Z with length C. So with this kind of arrangement, we have crystal. But what is unique here is normally in angstrom unit, protein this dimension. But what about our microscope? Visible light. Visible light order of nanometer. So roughly more than 1,000 angstrom. So our visual microscope is much larger than any single protein. That is the problem, and that is why we need X-ray rather than microscope to visualize proteins. Okay. So we have two completely different order of length scale. Here are several hundred angstrom, roughly, and another several 10,000 scale. And what about your drop size in well plate? Well plate.
Millimeter.
Yes, millimeter. Millimeter. 1 millimeter is 10 to the minus 3 meter, And 1 angstrom is which meter?
0 minus minus 9 12.
Here we have already have something here. So this is minus 9 meter,
Yeah.
and you can count. Yes. So 10 to the minus 10 meter, and 1 nanometer equals to 10 angstrom.
Yes.
Okay? So these are in the order of, in terms of angstrom,
Yeah.
and 7 times. So this is 100 angstrom level. Visible light is 1000 angstrom level, and actual drop size 10 to the 7. So these are, even if we take few micrometer under visible light, micrometer is
6.
and oh, is that correct? Something wrong. I made some mistake here. Sorry. Let's be specific. Oh, this is correct? Micrometer is 10 to the 4th angstrom. Because nanometer 0.5 micrometer. That makes sense. Okay. So these are important link. This unit, typical, let's say typical length for protein crystal, unit cell, unit length, 100 angstrom. Typical well plate size, millimeter, 10 to the 7 angstrom. 7 angstrom. And visible microscope limit, or very tiny crystal under the visible light, this size. So this size 100 times different. We should such a sense or feeling how small your crystal actually will be. So crystal is 100 times smaller than microscopic object. Okay. Then this is not visible under the light of visible microscope. These are the practical limit of visible microscope. So these ranges we are looking at with the help of microscope to detect or to observe what we have during protein crystallization. So these are crystal range, and these are not crystal range, crystal lattice. Single lattice or single unit, which are very regular in 3 dimensions. And these are crystal drop this size, and crystal, total crystal or whole crystal. These are crystal unit cell of this dimension. And whole crystal in its formation or under nucleation, which barely visible under the microscope and clearly visible in or maximum dimension in crystal drop.
Crystal
And we'll talk about how we'll practically make such a crystal drop as I showed you in first photo. Also, I'd like to develop some vocabulary with you. Here, figure, if you look at figure 1, basic hanging drop vapor diffusion. Which word do you know among basic hanging drop vapor diffusion?
So diffusion.
Diffusion, you know, also you know basic,
Basic. Yeah.
but hanging is hanging. This is hanging.
Yeah.
Drops are hanged on top of glass.
Yes.
So drop is drop. Drop.
Drop.
And vapor is gas state, not liquid state. So this is basic methodology to get a basic technique to get protein crystal out of your protein starting material, protein stock solution as well as precipitant solution. Here, if you look at figure 1, step 1, what do you have on top of glass slide?
This is a protein. Protein and
Here, look at color.
yeah.
These are in the same color,
Yes.
blue, right?
Yeah.
And here, those are same color in green. What does this
This is
mean?
target protein.
A protein stock solution?
Yeah.
And this is what you know. Out of your own protein purification, you may have your own protein in your buffer solution.
Yes.
That's what you have. But this is to change solubility
Solubility.
as a precipitating agent or simply precipitant.
Yeah.
As we change temperature for sugar crystallization, unlike sugar, we cannot play temperature very much with protein. Although, even for protein, we have technique to change temperature rather than this kind of precipitant solution. But to change temperature, we need incubator, many incubators or several incubators. Okay, but anyway, here as a basic technique to have protein crystallization, we are keeping temperature constant, and we are playing with precipitant solution here called precipitant with some additive or detergent. Okay, so these precipitant solution, those protein stock solution, is a basic hanging drop vapor diffusion. We are adding these two drops with equal volume. Look at figure.
Yes.
They are similar in size. Yes. Typically, if you pipette
Yeah.
your protein stock for drug screen, how much volume do you use for well plate?
Usually maybe just 1 or 2 microliter.
Yes.
Yeah.
Here also we are adding typical sizes. 1 microliter stock solution,
Yeah.
1 microliter precipitant solution. Okay. So they are same volume. We can vary the volume eventually, but right now in this figure, they are in same volume.
Yes.
One from stock solution, the other from precipitant solution. The trick here is, once we mix these two solutions on top of glass slide, we will invert them.
Yeah.
Originally, when we put them, it should be placed on top of
And then
slide and
turn
turn down.
Turn slide.
And what will happen then?
We can remove a solution,
Mm.
and maybe we can remain only the target protein, the protein we want to make crystallization.
That is a little bit tricky. As masters of science, I'm talking about your level of intelligence. Even for high school project, we can do protein crystallization. Actually, it happened with NASA-sponsored project for space crystallization. Actually, space protein crystallization. That's the project I was involved as a postdoc. But not as a beginner, you may be beginner in crystallography, but you are not beginner in science. Already you got bachelor's degree in biology.
Yeah.
Yeah. Also, you are studying this coursework. So you need to elevate your level of intelligence here. Okay? So based on this presentation, you already have an idea of barium. Typical barium for your own well plate is about 1 microliter. That's correct. There was written a few microliter or less. Okay, typical few microliter is 1 microliter, and turned down and closed. Then what is happening here is not losing anything except changing solubility. What means? What does diffusion mean?
Diffusion means
You told me you knew something about diffusion.
yeah. Diffusion it means we can get how to say this.
You can get some idea from the figure, middle figure.
Yeah. We can separate. We can separate some material in the mixture.
In mixture, yeah. Good word is mixture,
Yeah.
mixing,
Mixing.
mixing, and we need to distinguish diffusion in solution and diffusion in vapor. So here it's not about diffusion in solution. We have also diffusion in solution in later sections, but here it can be a little bit tricky for you to understand this figure because we are not thinking about diffusion in solution, but diffusion in vapor. So anyway, as you told, diffusion is about mixing. It's correct. So take that word with us. Any technical diffusion, the word diffusion from physics, not biology. But based on our own common knowledge about diffusion, your knowledge about diffusion, simply mixing to you, right? But in which way we can mix protein and protein precipitant, and what kind of result can we achieve? That is tricky part you should understand through this presentation. So basically it's cross mixing, okay? But diffusion in solution, really mixing in liquid, mixing two liquid, not by force or not by vortexing, but natural process.
Solution.
What is the driving force for such a natural mixing in terms of mixing in solution? Not mixing in solution, diffusion in solution.
Diffusion in solution.
Let's say you have two different solutions, solution A and solution B. Initially, you separate these two solutions with some compartment or well. By removing this well, what will happen?
It will have the gradient
Oh, another good one. Gradient.
Gradient.
Concentration gradient. Okay. A high concentration here, B high concentration here. Initially, if A and B are pure component, let's say here water and here ethanol or ethanol, and here no water, there no ethanol, but by removing separation, we have concentration gradient. Here A high, here B high, but eventually A, B will be the same by diffusion. That's the diffusion in solution or solvent phase or liquid phase. Okay. Point is, initially we have concentration gradient. Finally, no such gradient after mixing. Yeah.
There is no gradient.
No gradient because of equilibrium, equilibration. Okay. Same understanding can be applied here. But what is different between this diffusion and that diffusion is this diffusion in solution, that diffusion in vapor. Here, vapor diffusion, not solution diffusion. Okay, so here time is a little bit tricky part, so we will not discuss time significantly, but today we will focus in space. Solution, simple to understand based on your former experiences, but vapor, a little bit tricky. So we need to be specific in terms of locality or simply in terms of space. Here, space are homogeneous, no a physical boundary except this separation. Once separation is moved, no physical boundary except container, right? Yeah. Or in liquid phase. Or in liquid phase. No gas phase or no solid phase. Yes. But here, we do not have such a continuous phase. We have some discontinuity. That is tricky part of this dot there. Here, both are in solution. Yes. We put 2 drops, typically 1 microliter size, yes, on top of slide. And we turn down, initially up, yeah, at setting down. But because of its small size, not several millimeters, just few microliter, it will not fall down. Yeah. By surface tension, it will be attached on top. Then we will have some sealing. Yeah. And what this dot means is we have equilibrium, yeah, through vapor phase, not in solution phase or liquid phase. Imagine this. If we have some water, after a few days, what will happen? At room temperature, not under highly humid condition.
In few days.
Especially in dry condition. Hot summer dry.
Is the evaporation?
Evaporation. Yeah. Okay. Yeah. Likewise, initially, we put this and seal. We do not have any interaction with outer environment, but we still have interaction or transfer of some material or some metals within this confined or container. Here, still liquid precipitant solution. Here, mixing of these two. But this is close-up of mixed drop. Yes. Initially, we may have nothing, but eventually crystal will grow, as I showed you at the first figure. But during such a crystal growth, what is happening is transfer of these molecules. Anyway, we have molecules here and there. Major molecule here is protein, and major molecule here is precipitant molecule like NaCl or PEG molecule, polymer. Then also we have water here, water there. If we add in this way, water molecule is volatile. What is your own thinking now? You have some aha experience.
I connect with the evaporation water in this case, and I can understand the protein, our target protein, after remove a drop increase the precipitant remove and the final result we can get the crystal target protein.
Partly that's correct. Anyway, our end result should be crystal.
Yeah, crystal.
But what you are not clear yet is how can we manage it? So here, how can we remove?
Yeah.
You use the word removing.
Yeah.
How can we removing some extra solution?
Yes.
Okay. So you need to understand driving force.
Yes.
We will not remove water by scissor or pincet.
Yes. Just waiting, the water.
Did you say waiting?
Yeah, waiting.
Waiting, W-A-I-T.
Yes.
Just waiting, but how long should we wait?
I'm not sure.
That's the part we will talk about later, but from this figure, let's focus on spatial arrangement or arrangement in space. Now you have some question in your mind that will be answered soon within today's coursework. But first of all, you didn't have any idea about space beforehand. Now you have an idea about space in protein crystallization, particularly a dimension of crystal unit cell, simply repeating unit, and actual crystal size in such a drop. Drop microliter is actually, do you know, 1 microliter is which millimeter? Triple.
1 microliter.
Simply, these are another significant step. Simply, you know, liter is volume unit, right?
Yes.
And milliliter is another volume unit.
Yeah.
And microliter is another volume unit. Yeah. And milliliter is 1000 ml, right? Is another 1000 microliter. Then what is the unit in terms of millimeter triple? Millimeter. Simply, these are 10 centimeter by 10 centimeter by 10 centimeter. Yeah. That's the 1 liter of water, or 1 liter. These are 10. So 1 centimeter cubic. 1 millimeter is 1 centimeter cubic.
3 minus 3 minus 3 minus 2 minus 9. 1 microliter. 1 microliter is 10 minus 9 centimeter.
What is 10 minus?
9.
10 minus centimeter?
Yeah. Millimeter.
I'll give you quick answer. You are a little bit confused. to save our time, I'll give you answer. But first of all, think about the drop size of your protein solution or any kind of solution you transfer through your pipette.
Yeah, just 1 microliter, or a few microliter.
In terms of millimeter size.
Millimeter, a millimeter, just 1.
Yes, just 1.
Yeah.
Is 1 millimeter cubic.
Yeah.
These are consistent. 1 ml or 1000 micrometer, actually 1 cubic centimeter, right? 1 cubic centimeter is 10 millimeter times 10 millimeter times 10 millimeter, right?
Yeah.
So 1000 microliter. So 1 microliter is, by definition, 1 millimeter times 1 millimeter times 1 millimeter times result in 1 cubic millimeter. That's the size you can observe with your pipette transfer. If you transfer, actually drop is not square form, it's not cubic form. Unlike crystal, water drop or solution drop can be a sphere. At the tip, it can be deformed into longer form or ellipsoidal form, but once from the tip, it can be sphere. But in the glass plate, it can be dropped like this. It's order of 1 millimeter size, right?
1 millimeter.
So that's the practical concept you should develop.
Yeah, in space.
In space. Okay. And let's come back to this. So here, microliter is close to 1 millimeter in dimension. So we would like to have protein crystal in terms of mixing protein solution with precipitant. But here you do not know how crystal is formed with removing water, extra water out of such a mixing drop. Okay?
Yeah.
But here, if we add 1 microliter, what will be the volume, final volume, initial volume? Yeah.
Yeah.
Roughly.
Double. 1 microliter, same volume of protein solution, and one is the one volume from precipitation patent solution. I got two times of the
Yes,
volume.
2 times.
Yeah.
So simply 2 microliter. If you add 1 micro plus 1 micro, 2 microliter. So here, amount of protein in that drop will be the same.
Yes.
We have protein only from this side. We have precipitant from this side. So amount of precipitant chemical and amount of protein will be the same before mixing and after mixing, but volume here will be doubled.
Double, yeah.
So concentration will be half
Half. Just
before mixing, after mixing.
after mixing.
Yeah. That is the part, and the reason why it can be crystallized will be explained later. Anyway, have an idea about mixing and arrangement in space. Precipitant solution at bottom and mixed drop on top, and in between we have gas phase.
Yeah.
Here, this denotes water from mixed drop
Yeah.
to precipitant solution. So actually what we are expecting is dewatering. So water will be transferred from mixed drop to there, down there. That will be the answer you asked, how we can remove
Yes.
something out of drop which can drive crystallization, but we are not removing any precipitant solution there. We will remove water out of mixed drop. Okay. And that is basic hanging drop vapor diffusion. And this is the plate we talked about. What is this plate?
Well, 24 well plate.
Yes, 4 by 6.
Yeah.
4 times 6, 24 well plate. What is this? As your guess, 96. They are typical size
Yeah.
which are using at the lab. Here, if you look at the well plate closely on your textbook, this is not like that. This is kind of a typical one, but this has some custom design in terms of shape in each well. So-called not just well plate, but crystallization well plate, specialized for sitting drop or hanging drop and some custom setting. Here we talked about hanging drop, but here sitting drop.
Sitting drop.
What does that mean? Sitting drop.
Sitting, it means last time hanging drop our protein in this side.
Top.
At the top and we turn slide like this. But in this, just I guess.
Hey, guess.
Yeah.
I appreciate your guess.
In this case, maybe we just stand the plate like this and
So, as you told, drop here, hanging drop.
yeah.
Drop here,
Sitting.
sitting drop.
Yeah.
Exactly. That's what we have. So, hanging and sitting is a way to distinguish these two settings: vertical,
Vertical.
stand up, or hang.
Hang.
Simple. Now you are building confidence in vocabulary. So, if you look at the 94 well plate, you may see design like this. And drop here, and solution here. Okay, so we can have sitting drop, far from, not very far from, but beside to precipitant solution well, drop, and they should be covered with some film or sealing. Okay, each drop can be manipulated in this way, so we can have both settings: sitting drop and hanging drop. Anyway, this is about crystallization plates.
Yes.
Okay. And not to be specific about crystalline setting, let's talk about general workflow. So for what is your experience in purification?
Purification.
Any you'd like to learn something about purification too?
I would like to know how to get good condition for purification, protein purification. Because sometimes I have a trouble with purification, protein purification.
What? Chopper?
Yeah.
Chop?
I have some problem. I can.
What do you mean by chop?
Chopper.
Chopper? What is the
Chopper.
spelling for chopper?
I mean, really difficult for me to get the purified protein.
Your difficulty is first and
Yeah.
purity of protein.
Yeah.
But what is chopper?
Trouble. I get some trouble.
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 Ah,
Sorry.
sorry. Trouble
Yeah.
to get purified protein
Yeah. Right.
in high purity conditions.
High purity.
What is the opposite of purified protein or high purity protein? What is hindering your purity, or what is degrading your purity?
I would like to get high concentration of my protein. The final target protein.
Mm.
I have some experiment. I have to get very high concentration protein
Mm.
and apply this protein for some to detect my protein, the first my gene have to expression or not. So I just confirm by purification.
Yes, you'd like to confirm
Yeah,
by purification.
but sometimes it's really difficult for me.
Mm.
So I would like to learn more about it.
So let's develop some vocabulary
Yeah.
about your trouble. Without having proper vocabulary, even we cannot present our difficulty
Yeah.
to others,
Yes.
even including your colleagues or your PI
Yeah.
or professors.
Yes.
So first of all, we can erase this, and any typical workflow, you can read the text, but in the text, you may not have proper vocabulary to describe your trouble.
Yeah.
That is our trouble. So we need to build some way to explain our difficulty. Okay, let's take that position together. So first of all, your concern is purity. You'd like to demonstrate your purity, but you had problem in terms of getting highly pure proteins, and you'd like to describe the troubles. Trouble may be single or multiples.
Yeah.
So it's better to say troubles to get high purity. This is kind of grade. High purity protein. Highest purity is like that. Crystal quality protein.
Yeah.
If it is crystallizable, any high purity protein. But what is hindering your high purity proteins? At each step, I said at each step. Here we have some steps, and you talked about expression. Firstly, we may start with gene sequence,
Yes.
and we may have recombinant one,
Yeah. Right.
not natural one. So expression can be first problem. First of all, we should have expression for recombinant one, otherwise we cannot proceed. But at expression, do we really have purity problem?
Because in expression step,
Mm.
I can control
Mm.
this step by color, because the color I can see the change in color when I make cell culture.
Mm.
I can control expression step.
Expression step.
Yes, I know expression, spread,
Mm.
but I'm not sure is spread much or not much.
So here, your trouble is expression level actually,
Yeah.
not purity.
Yeah.
You'd like to establish overexpression with your vector.
Yes.
Time to time, you may fail to get overexpression due to some problem, either in vector itself or in cell. So we may not have enough amount. But once we have overexpression, we have target protein as well as other proteins always, because they are in the cell. In the cell, we cannot talk about purity. Always we.
What generate?
Mm. So at expression level, we can talk about only overexpression. Overexpression or not.
Oh yes.
So here at expression level, we cannot talk about purity, because we are dealing with cells. As cell, we cannot separate our target protein from cell. Proteins are in the cell. Whereas we have other proteins or even other macromolecules, even other molecules like lipid or carbohydrate. Okay, so expression level, what you talked about is overexpression. Overexpression is another topic, so I'd like to focus on purification. But after expression, what do you have in between expression and purification?
Lysis.
Lysis. Oh, very nice. Cell lysis, break down the cell.
Yeah.
And you are extracting your target protein.
Yes.
So, what step did you do after cell lysis to get your?
After cell lysis, our centrifuge.
Centrifuge.
Yes.
Through centrifuge, what did you remove?
I removed the buffer. Cell lysis buffer.
Mm.
And the cell wall.
Cell walls.
Yeah.
You removed cell walls. Simply cell pellet.
Yeah.
In that case, what was your assumption behind such a separation? Where should you have your protein, target protein, in the cell lysis buffer or in the cell pellet? I'm asking this question because you told that you would like to remove lysis buffer.
I'm sorry. I will remove the pellet.
Pellet,
Yes.
solid part,
Yeah.
after centrifuge.
Insoluble part.
Insoluble part,
Yeah.
cell pellet insoluble part, and you will have your target protein in solution, supernatant, so-called supernatant.
Yes, right.
So first step is any expression level is not our focus.
Yes.
This is beyond protein crystallography. This is topic of your molecular biology.
Yes.
So that is another topic. But in the chapter proteins for crystallography, we may cover something about overexpression too.
Yes.
But right now, for crystallization purposes, let's check the process with which we can get high purity protein for crystallization setup. Okay, so after cell lysis, what do you have? Supernatant, you said.
Yeah.
Supernatant. Simply soluble part.
Yeah.
Here we have lots of mixtures, whole proteins, whole soluble proteins. So this is not high purity protein. Even this is not medium purity protein. This is very low purity or highly mixture protein. Okay. After this step, what do you do?
I will choose one kind of column, purification column.
So, 잠깐 이게 없어져 버렸네. Purification column.
Yes. For example, NTA column.
Purification with column. Nickel affinity.
Yeah.
That's what I do. What kind of purity level do you expect after nickel affinity column?
Because in for example, in my some kinds of protein, I'm insert in with PET28A vector, and it containing the
histec for crystallization, overexpression of target protein in crystallography. Yes.
And then I use the NTA nickel column to detect Only my target protein.
Only your target protein. That's very correct from the perspective of purification. Nickel affinity column for his-tag recombinant protein is the very way we are using for protein crystallography. So once you have overexpression, straightforwardly you will have the final target protein with his-tag. We will talk about his-tag even today. His-tag. 6 his amino acids successfully with some extra amino acid for connection.
Yeah.
Okay. But his-tag, I'll tell you something about his-tag. You may have another troubles even to get such a his-tag protein, but even with his-tag purification or nickel anti-affinity, we may not have enough purity for crystallization. This is preliminary step. For high purity, let's say 99%, then his-tag may be 90%. This is rough estimation. 90 may be good enough for some enzymatic assay, but 90% may not be good enough for crystallization. But you may have even difficulties to get this level. What difficulties or troubles did you say in between, except overexpression? Did you have difficulties?
Purification.
Even his-tag purification or?
Purification with his-tag column, because sometimes after purification, I run SDS gel, acrylamide gel, and I cannot get the target band.
Target band.
Yeah. So it means my purification step is not good.
That is the level. You should check here, even expression level.
Yeah, together.
Let's be practical. I do not have example today, but anyway, we are developing our vocabulary to describe your troubles to get target protein of high purity. But your problem is not to get high purity, but even get expression itself, to get overexpression itself. If you have trouble in his-tag purification, as I understood your problem, it was not the problem in his-tag purification itself. It's the problem already in overexpression. What you're saying is SDS gel learning as a way to check. When you have SDS gel learning, you have some molecular size marker and loading sample, and you may have some control like a flow-through, but in terms of loading sample, let's say your target protein of some kilodalton here, okay, let's say 100 kilodalton, okay, then surely you will have your target protein in the presence of other protein. Okay? But because of your induction, you know the word induction. What chemical do you use for induction? IPTG. Before IPTG induction, we may not have your target protein in high amount. But after IPTG induction, all cellular mechanism for such a given cells are working to produce the target protein with a built-in mechanism for protein overexpression. So once you did apply IPTG for protein overexpression induction, you should have target protein already in loading sample. Here.
I got it.
Mm.
I myself like to describe
Mm.
in the supernatant.
Supernatant.
Psoriasis, I got the target protein band,
Mm.
but in my case, I purified by very condition of imidazole.
Imidazole.
But just some of them, just 1 or 2 condition, maybe 20 millimole imidazole in a washing buffer.
Then you need to check flow-through.
Yeah, right.
Here, not only loading sample,
Flow-through.
but also flow-through. During washing step,
Yeah.
you might lose whole or major part. So, flow-through, so-called FT, flow-through.
Flow-through.
Loading sample flow-through, you need to check both. If you lose many in, anyway, first of all, if you lose your target protein through washing step, but still loading sample from supernatant, right?
Yes.
Here you should have them.
Yeah, I got it.
Mm.
I got it. But in flow-through,
Mm.
it should be there is no my target band,
Mm.
but it's a little bit.
A little bit.
Yeah, a little bit in flow-through, a little bit in illusion
Mm.
solution.
Illusion solution.
Yeah.
Mm.
So I think my purified step is not good.
I cannot say something specific in this case, but we need to separate, or we need to check
All
2 things, I think. Firstly, before doing any histec,
Yes.
you checked SDS gel learning of supernatant, even at expression test, right? At that test, you may have some proof
Yes.
of overexpression, but when you do nickel histec affinity column in your loading sample, did you have same amount of target protein or not compared to expression level test?
Actually, it should be my target protein should be very big band.
Very big band.
Yeah,
Mm.
but it's not big.
So you may not have same condition in purification step and expression step.
Yes.
Usually we are doing expression test at smaller scale in terms of cell culture. Then we made more volumes of cell culture for purification step. Between these 2 steps, you may not have same induction, or you may not have same overexpression. So you should reproduce what you had at expression level test. So without having enough amount at loading sample, you cannot recover through nickel affinity column. So your problem may be in different conditions of expression and purification. Okay. So simply, this is not purity problem. This is overexpression level problem.
I will try.
Anyway, that is your former experience. But in this coursework, we actually what we are discussing is not what you did before, but I'd like to help you to describe your problem in specific terms. We are trying to distinguish overexpression problem against high purity problem. For crystallization, what we are trying to secure or confirm is high purity. But what you had before is not purity problem, but expression problem. In between expression stage or purification stage, you couldn't keep proper overexpression. it's not about purity.
Yeah.
It's about expression.
Expression.
Okay.
Yeah, I got it.
Also for expression, your case is you said expression was okay, but even if expression is okay, we may not have enough amount in SDS gel learning because of solubility problem.
Yes.
As you said, as you described in cell lysis, we may not have soluble protein even after expression. It's very probable with some membrane protein or some proteins which need some modification. So, otherwise, we should have soluble protein. Anyway, we should have some soluble part of our target protein. Okay, once it is made in soluble form, there should be no difference between expression test and loading sample of nickel affinity column. They should be identical. They should be different only in terms of amount scale. This may be in milliliter level in terms of culture. This should be in liter culture. Then out of liter culture, we may have several milligram,
Yes.
several hundred or several 10 milligram, okay, with in E. coli, several milligram in human cells.
Yeah.
Okay, but anyway, even though you have good amount of overexpression here, still we may have purity problem. That point I'll talk about from now on. After HISTEC, we may have 90% purity. Still, we may have some unclean band before and after loading sample, but before loading sample, before HISTEC, before loading sample, target is minor,
Yeah.
but after HISTEC, target will be major, like this way.
Yeah.
Above and below mostly removed, but still we may have some paint peak band like this. These bands can be removed with further purification, like ion exchange or gel filtration. But did you do that?
Not yet.
Not yet. But for practical protein crystallization, we need to achieve, as said, 99%. To do that, we should remove such impurities. That's the problem of maintaining high purity protein, as I told you. But your problem is not purity problem, but expression problem.
Yeah.
Okay. But anyway, to achieve protein crystallization, we should have 99%, nominally 99%. Okay. And
Very high.
yeah. But for chemicals, we have higher purity, not for proteins, but for even IPTG or any, even ethanol.
Yeah.
For research grade, we have 99.99
Wow.
or several 9. So that should be chemical grade, but protein grade, we cannot achieve such a high purity because of cell-free impurity.
Yes.
I'll not talk about cell-free impurity further, but proteins can be vulnerable. It can be degraded in terms of amino acid. They are not strong as other chemical bonds, so they can be broken. So even in SDGL learning, we also another problem, dimer
Dimer?
or multimer, we have some aggregation. They can be self-impurity. Let's have some break.
Yes.
And here we start gene X or protein X. Gene means your construct, and X means some name.
Yeah.
Here, unknown gene or unknown protein. So, question is whether you have soluble protein construct. That means we may have insoluble construct. Simply construct can result in soluble or insoluble. So we should design our protein sequence according to expression test. After expression test, what we actually has is soluble part. Your supernatant,
Yeah.
insoluble part. So by changing construct, you can play with resulting protein in supernatant, either in soluble part or insoluble part.
Yeah.
Okay, that's the part you should play with as a overexpression test. Okay, then if you have soluble protein, then we can express and we can prepare. Here, such a things are simplified as a gene X or protein X. Then we can set up crystallization plate once we have protein solution. Such a steps are squeezed here, somewhere here.
Yeah.
Many things are hidden. So we need to expand when informations are squeezed in this way. When you had difficulties, think about what you need to expand.
Yeah.
Problem you had was not a purity problem. There was an overexpression problem. But if the explanation was too brief or steps are too squeezed, you do not have room to explain. So extend the problem and reserve a room or make a space for you to explain the problem or troubles. That's the lesson I'd like to share with you. And here, rather than expression, many things are explained in detail in crystallization and diffraction experiment. Here, blue one, set up crystallization plate, as we discussed, 94 well plate or 24 well plate we may have. Also, we can have some custom designed one, hanging drop or sitting drop, and store crystallization plate. Where?
Yeah.
Here, store means some place. So you should be aware of place, space, and time
Yeah.
in between. Set up crystallization plate means we are mixing protein solution,
And some reagent.
precipitant one. And
Precipitation.
then we should store such a plate at some place.
Yeah.
For us, we have crystallization room.
Yeah. What temperature for?
Oh, very nice question. That's the point. Either at room or incubator, we can maintain such a plate. Incubator, we can maintain temperature individually per incubator. But we cannot change the room temperature easily. For single room, we should have single room temperature. Otherwise, we have too much variation.
Yes.
So our room is kept at 18 Celsius, I think, around 18,
Yeah.
with the variation of 1 degree. Anyway, we can control such a room temperature. Okay, just before X-ray room or before washroom, we have such a setting, crystallization room. Anyway, once we have crystal, first of all, we should watch the plate with microscope.
Yes.
There is a photograph at the textbook. Anyway, with visible microscope, we can watch several hundred micrometer size or point few millimeter. Okay, of drop size is close to 1 millimeter. Okay, then if you have crystals, mountable crystals, here mountable means for diffraction experiment. Simply visible. Mountable crystals observed means visible crystals. By being visible, crystals should be much larger than few micrometer. Okay? At least several 10 micrometer, at least. Several 10. Let's say 0.01 millimeter, maybe minimum by routine observation. 0.1 millimeter, quite visible, but 0.01 millimeter may not be quite visible because of some aggregation or some not very transparent drop. Okay, but also 0.01 millimeter is too small for routine X-ray, but 0.1 millimeter quite feasible. Okay, old days in early 60s or 70s, we should have millimeter size crystal, but nowadays with the powerful X-ray source like synchrotron, smaller one will be fine. Okay, but anyway, it should be visible. Unless visible, how you can identify your sample crystal? So visible is crucial step with current X-ray technique. We have some aid in terms of dye or UV. There is explanation there because time to time we cannot distinguish protein crystal from salt crystal because we are using salt like NaCl to introduce to change solubility, and not only protein crystal but also salt crystal can be formed. So at this step, even if crystals can be observed, they may not be protein crystal. Simply they are not mountable crystal for X-ray. So we should check. Okay. Then if you have mountable crystals or good size crystal and good quality crystal, I'm talking about visual quality, then mount means transfer sample from well plate to X-ray machine, sample holder, then collect some images. Okay, good diffraction. Okay, we will find cell parameters, cell length here. Here, millimeter scale or sub-millimeter scale, several hundred micrometer. Here, cell parameters or cell constants in angstrom, maximum around several hundred angstrom. So, in terms of micrometer, it's a sub-micrometer. Okay, so these are order of experiment. In between, unless we have, even if visually okay, diffraction may not be okay, then we should go forward. Also, another chance is if you have, as I showed you in first figure, we may have multiple crystals out of single drop. At that case, pursue next crystal, okay, but with different cryo buffer. But we will not talk about cryo buffer by now. There is another complexity involved in diffraction experiment. Diffraction experiment, normally for protein crystals, we will pressure cool the crystal. Simply freeze the crystal. So like the cell, equalized cell stock, we freeze the cell with ethylene glycol. What do you do with your equalized cell for storage?
Storage. Equalize. I use glycerin 100%.
100% what?
Yeah, 100. 50% glycerol.
Glycerol. I made mistake. Glycerol. It was glycerol. Like E. coli storage in deep freezer, we can freeze the crystal.
Yeah.
So-called 잠깐 스탑요. 꺼져버렸네. 케어를 안 하면 꺼져버리네. 이쪽을 보고 해야 되나? 그렇구나. BNC가 아니고 RGB인데. 오케이.
다시 촬영해도.
예. Glycerol will be used not only for cell stock but also for freezing the crystal to prevent radiation damage through diffraction, X-ray diffraction. We are using glycerol or other cryoprotecting material, chemical. Okay, that's the process. And routinely, from crystal down to diffraction, we are going through the workflow. And if we do not have good diffracting crystal, we should design, or we should set up crystal again, or we should change the cryo buffer when we have problem in terms of cryo cooling.
Yes.
Okay, that's that process. In that case, if we have good diffraction but cryo problem, then we will change the cryo buffer. But otherwise, we should pursue another crystallization setting. Okay. And this is the photo for lysozyme. 이게 또 꺼지네. 죄송합니다. 이게. We have some instability problem here. Okay. We are coming back. This is the figure I already showed you. 다시 찍고 계시죠?
네.
예. And this is the figure I'd like to talk with you. And this one, I'd like to have your attention. Here, this is in rough presentation, also imaginary presentation in 2 dimensions.
Yes.
These are figures drawn with real geometry, protein geometry. Here, can you notice this kind of empty space?
Empty space.
Empty.
Empty.
No cross contact.
Yeah.
And here, in terms of angstrom, now again, in space, carbon bond, roughly 1.5 angstrom.
Yeah.
Okay, and carbon oxygen in CO 1.2 angstrom, and HO in water around 1 angstrom. So we have dimension like this, 1 angstrom. Okay,
Yeah.
then here we have kind of interaction between each molecule, each atoms, either with bonding or non-bonding. So they are not far from each other. Okay. Also, here, what is shown here is histag. Okay. Histag is flexible by its nature, but even it can be part of soluble protein. And even without cutting such a histag, it can be crystallized as a whole protein. Then within the crystal unit cell, we may be able to see such a histag part.
Yes.
This is what is shown here. His stack, can you notice this? 1, 2, 3, 4, 5. We have 6. Okay, 6 his amino acid.
Histidine.
Yeah. So this is showing 6 his stack attached to target protein.
Yeah.
Okay. In reality, atoms are in cross distance through bonding. Also, even if we do not have bonding between histone and the other part of protein, we still have some packing, cross contact.
Yeah.
But here, what we are missing here is, let's say, alpha helix.
Yeah.
Diameter of alpha helix is around 3 point something angstrom,
Yeah.
and here this is multiple of several 4 angstrom. I think, let's say 20 angstrom or more. We have too many vacant space. I will tell you one thing as a caution.
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 Yeah.
Warning, simply. This is about textbook story to explain some idea. Here, as I told you, this figure is not based on reality. This figure is prepared to give you an idea about arrangement.
Yeah.
You should take such a concept, but you should be aware of such a misconcept or mispresentation or wrong presentation of reality. Okay.
Yeah.
So here, this is nice in terms of give us idea about packing, but this is wrong in terms of lack of interaction.
Yeah.
This kind of crystal cannot be formed because we have too many things in vacant space.
Yeah.
It may be occupied by water because always we have waters bound to protein. Without water, protein cannot be stabilized. So always we should have water inside of protein crystal. That is very unique character of protein crystal. Even waters are like fluid.
Yeah.
It doesn't have to be in regular position. It can be fluid like nature because water molecule, 1 angstrom can be much smaller than protein itself. It can go through even beta sheet and alpha helix. Okay, so it can go through even some channels. It can be space for water, like a potassium channel or some calcium channel. It can be a space for such a water as well as some ions. But otherwise, it should be occupied either by protein or water. But these are too fluid. If you have only waters in between, crystal cannot have some strength to be stabilized or be formed in regular position. So simply because of that, this is not very real presentation of protein crystal packing. But if you look at some details using real model is like this. His stack cross to other amino acid within protein. Even here, if you look at something here, additional protein, additional solvent molecules can participate such a network. So we may have some water molecules around his stack, water molecules are protein. So in such a way, we need to develop some idea about space. Okay. In angstrom unit. For crystallization, we talked about space in millimeter scale. In between, we have some micrometer scale. Okay, so here, typical lysozyme is typical, very well crystallizable protein, and we can buy lysozyme out of some commercial vendor. So even it can be ground to millimeter scale. Okay. Still, we have angstrom level. Let's say 50 angstrom in ABC dimension. Okay. 잠깐 포즈 좀 해주시겠어요? Let's have some. Let me have some feedback from you. I talked about space.
Yes.
What about your own understanding now? And I'll shift to phase diagram and I'll talk about something in time.
Yes.
So we will finish it soon,
Yeah.
within hour and.
In space,
Hmm.
in the space, crystallography, not only protein, and there are some
잠깐
empty
이렇게
space.
네.
좀 다시 시작해 주실래요?
네.
예.
하고
하고 있어요?
네네.
예. Sorry. 예.
There are some empty space, and in
Empty space.
empty space,
음.
water
음.
will be through all of empty space in.
That's the very feedback I'd like to hear from you. There is no empty space. I'm giving you answer. That's the misconception that I'd like to correct. There is no empty space in protein crystal. Every point around 1 angstrom will be occupied by some atoms.
Some atom from a lot of structure, protein structure, and they will be occupied together.
Let me say in this way. Is there any empty space in protein crystal? Okay?
Yes.
Then my answer is no. Simple answer is no. But how empty it is? So empty means empty, the word empty should be described in terms of length scale.
Yeah, length scale.
Okay?
Yeah.
Length scale. So if you are saying around 0.5 angstrom or even 0.1 angstrom, we can find some space which is not occupied by any atom.
Yes.
But if you are saying around 2 angstrom or 3 angstrom, that's the typical resolution range of X-ray method, then no empty space.
Yeah.
Either protein itself, amino acid from protein, or water,
Yes.
or any other ions or ingredients will occupy such a space.
Yeah.
Although most cases water will not be part of protein presentation. That is the tricky part.
Yes.
That is why I showed you two figures simultaneously. One from Histech,
His
the other from two-dimensional
dimension.
packing.
Yeah.
If you read textbook by yourself,
Yes.
you may develop some misconception, simply wrong concept.
Yes.
That's the very point I'd like to avoid with you. This is very critical. So, simple question is no empty space, as you might think, but such a space should be either occupied protein or water, mostly water. Water. Also, think about what we did with crystallization. What we actually did is dewatering. let's say this way, water and protein and precipitant. Three major players in protein crystallization. Also, three major players. If you take out precipitant, water, it can be precipitant, but vapor.
Yeah.
Precipitant can be part of vapor. Okay. Vapor chemical, simply. Either precipitant or vapor chemical. So, most significant molecule in life is water. And the target molecule we would like to study is protein. And extra one is some vapor or extra chemicals. If you take away this for the time being, mostly protein with water. But pure protein may not be stable with pure water. Yeah. So stabilize these two, we may still need vapor. Okay?
Yeah.
But in terms of space, water should be present unless the other two are occupying the space.
Protein and buffer.
Protein or other chemicals.
Yes.
Let's say either precipitant or vapor as other chemicals.
Yeah.
Neither water or protein. Okay? Also, through protein crystallization step, what we are doing is controlling water. That's the topic I will proceed quickly.
Yeah.
Because we already covered major issue. Also, dewatering, removing water
Yes.
out of drop has some timing issue. Quick dewatering means quick crystallization or quick aggregation.
Yeah.
Slow dewatering or removing water in slow manner may result in better quality crystal or no crystal at all. Okay?
Yes.
So, removing water or dewatering can be critical
Yes.
for you to understand protein crystallization. That's the key concept I'd like to share with you. Such a concept maybe it's not wrong in the textbook, but it may be given in wrong manner
Yeah.
because of omission in the figure, like ribbon diagram. Okay. And let me come back here. Okay. And this is two figure I'd like to emphasize. Simply, this is good for you to understand arrangement
Yes.
in regular manner, but this is wrong in terms of lack of
Space.
interaction or missing water or missing interaction between protein and other chemicals,
Other chemicals.
including water. Here, this is more realistic because 이게 참 말을 잘 안 듣네. 다음번엔 다른 데서 해야 되겠네. 참. So to save our time, I cannot rely on PPT today. So also we are approaching the time. So I'd like to make some quick summary for you. Main concept.
Yes.
The part I'm missing here is a solubility diagram
Yeah.
to describe the watering process. Okay.
Yes.
The essence is in terms of solubility is if you look at textbook, protein concentration
Yes.
and precipitant concentration. And we have curve like this. Previously for sugar protein, not protein, sugar, we have temperature versus
Yes.
sugar concentration. But here we have precipitant concentration and protein concentration. Both are in water. We may dissolve such a buffer component or precipitant component in water as your way to prepare buffer or precipitant. Also, through cell lysis down to histec and further to gel filtration, we have protein in buffer solution, right? So, water in buffer solution. Okay, so if we have protein stock solution here, protein stock solution and precipitant stock solution here. Let's suppose if you add these two, initially protein here, but precipitant here, but by mixing these two, let's say 1 microliter of P, 1 microliter of C, precipitant.
Precipitant.
We do not have good spelling there. What do we have? Same P.
P. Precipitant.
So protein, even PR same. So it's better to distinguish these two anyway. So let's say a stock and this is any, let's call C anyway. And here, if we add these two, volume will be 2 microliter, for example, but amount will be the same. So concentration will be reduced down to half. And this one also will be reduced. I'm not good in scale, but okay. So by mixing, let's say we have two drawings like this. Not this, but this. This can be called solubility curve. Solubility curve. So initially, protein stock solution enough high concentration, which can be crystallized in the presence of precipitant. But by mixing, concentration will be half. So these are in soluble region, although these are insoluble. Soluble, insoluble. So if solubility curve is like that, by mixing protein stock and precipitant, it may not be in insoluble or nucleation region. So by being in nucleation, it should be in precipitant in quick manner. That's the timing issue. If we put sample in harsh or extreme condition, it can be precipitated in quick manner. But if we cross to soluble these are in equilibrium, but they are not in equilibrium. So we are not gently changing condition, but if we push here, it will be aggregated rather than crystallization. So out of soluble region, but in insoluble region, protein can be precipitated rather than crystallized. It's not insoluble, so it should be something else. Something else cannot be crystallized in such an abrupt or rapid change. So rather than in good nucleation, it can be in aggregate. But here, they are insoluble after mixing because of half protein, half precipitant concentration, but because of dewatering of this drop against mud liquor or stock solution of here a drop and this stock of precipitant. Here still solution is concentration C. Here half of C. Because of this concentration difference, as you described in liquid phase diffusion, same concentration gradient we have. This is double of drop 1, or simply drop is half of bulk 1. So we have transfer of water molecule from drop to stock or bulk. So we are actually dewatering of drop solution by transferring. Transferring is not by our hand. Transferring is by equilibration between this drop and this bulk. Okay? This is the dewatering process happening in hanging drop and sitting drop vapor diffusion. Okay? There will be further explanation in other crystallization setup, but basically this is the process we can experience. I'm sorry not having PowerPoint, but in the essence it's like this. So main concept is playing with water. There is an ambiguous explanation about this process in the textbook, but essence is like missing of water molecules in space. Here there is a missing explanation involving water transfer. Actually, we are not removing protein out of this drop. Protein will be there. Also, we do not remove precipitant chemicals there. Precipitant chemicals in the drop, in the mixed drop, will be the same. But by reducing total volume, initially 2 microliter, but eventually it will approach to 1 microliter. If you read textbook, there is an explanation why we should approach it to 1 microliter as a final volume. So if you remove the volume down to 1, protein amount same, but back to original volume. Precipitant amount same, but back to original volume. Then what we are going is like this. Initial setting here, but we are approaching this way. But unlike setting right there, by mixing double concentration of protein and double concentration of precipitant, we start here, and by water transfer between these two regions, these are not very quick. These are natural process due to diffusion. Diffusion is in equilibration. So unlike direct mixing at this point, starting from here, diffusion will drive here. So through this process, we have gentle change of solubility. So around there, around solubility curve, we can experience gentle nucleation. even if that is a little bit quick, this way, nucleation. So we may not go in extreme case. Near to solubility curve, we will go through gentle nucleation. Always we need gentle nucleation and gentle aggregation, not quick aggregation. Quick aggregation will result in quick aggregation, not crystallization. But gentle aggregation may result in good crystallization with good nucleation. Okay? That's the point I'd like to share in terms of timing.
Yes.
Also in terms of driving force behind this kind of now this is back. So here this is the reason I talked about,
Yeah.
and I'll show you further. We have variety of I'm sorry. Next time we should change the place. Here, this is the step described in the textbook. Starting point here, and this is gentle diffusion process.
Yeah.
And here, no good place. This is too quick aggregation, so we should avoid such a place.
Yeah.
But this is not physical space. This is the space in phase diagram, okay, which has something in time.
Yeah.
Okay? Because of computer problem, let's finish it today. I have other materials, but I already shared main idea.
Yeah.
Main idea is from the perspective of crystallization, please think in terms of space,
Yes.
also in terms of time. In space, we have very different times,
Different.
length scale, millimeter scale and
Angstrom.
angstrom scale. Okay, in between we have micrometer scale
Yeah.
with visible microscope. Also in time, don't forget about dewatering.
Yeah.
Also in space, don't forget about water, presence of water in protein structure. If you have those points in your mind, you can decode what was missed in textbook explanation.
Yes.
You can build correct picture. Okay. Also, as a tip, in practical tip for your own research, when you have troubles, that's the word I did have difficulty to hear at right beginning. But anyway, there is another level of difficulty in English language as a second language. But when you have difficulty, we need to articulate. Do you know the word articulate?
Articulate.
Last time I talked about the word articulate with others, but articulate is the joint in our body, also rhetoric in our language expression, also kind of exaggeration in our speech, using different tone to deliver some emphasis,
Yeah.
or use different speed to give you a good feeling. Likewise, time to time, as a practical researcher, we need to articulate our topic for discussion. Your topic is like this. You thought you had difficulty in protein purity. But as we discussed, the difficulty was in expression. But at the beginning, you cannot bring the issue properly because something are squeezed in small space.
Yeah.
Then we need to expand such a space in bigger space. Then we may have room for discussion. Also, if we are missing some parts or component, some parts or some topics are behind the scene. So we need to bring such behind the scene players into playground,
Yeah.
or action point.
Yes.
What we are missing from protein crystallization discussion in the textbook is water.
Water.
Diffusion is
Watering.
water molecule. Diffusion process is all about Vapor diffusion is all about water transfer between drop and bulk.
Yeah.
And also, water molecules are completely mixed in packing. We don't have such an empty space there. So we should talk about water in crystallization. Okay. That is the main point I shared with you. Today we will not have any quiz, but let me continue next time with quiz. Thank you so much.